This is the monument itself. This little ball here on the ground, the top of that is what the monument was measured for by the surveyor. So when we take our measurements, I held the handheld on the ground about this level so it could still have the fix on the satellites, the offset GPS. We also had to do it ground level right in the center here. So laterally, they'll still be accurate, but we can't put those inside the ground. The RTK unit can actually take the measurement on the very top of that monument. Okay, so we're out here with the offset GPS unit, and this GPS unit is used when you need to survey a lot of different items at the same time. So you can stand out in one place and shoot a lot of different objects just from one spot. But it also has the effect where you can you avoid the multipath error where you would normally get from standing underneath a tree or right next to a building. You can stand out in the open where you have a really good signal from the satellites, so that your numbers are a lot more accurate than if you were trying to go underneath the canopy or go next to a wall. The unit itself is pretty neat. It's a lot larger than a normal handheld, and the reason for that is here on the front it's got a laser device. The laser goes out one direction, comes back in the other, and this actually shoots to the object that you're trying to measure. And then this other smaller bit here is the camera, and the camera you don't need to have, but for survey applications it's handy that when you click the point to take your actual measurement, it takes a picture of the object, and that can be very helpful when you have a lot of different points and you aren't sure which is which. You can go back and reference it. The laser is really accurate, and the machine does all of the trigonometry calculations instantaneously in there, so that when you're looking at some object, it will tell you on the screen how far away it is, and then when you take the point, it does all of the math automatically. So if I point the device upward because I want to get the measurement of, like, let's say the smokestack on the building behind us over there, this will take that measurement instantly and give us, then do all the math, because we're looking up at at a steep angle. It's not like looking straight and level where there's no angles and distances to calculate, hypotenuse. That's pretty much an introduction to the offset GPS itself, and then we can look at the screen here. Okay, so we're out here now with a handheld unit. This one is, I'm not a sponsor for Garmin, but this is the Garmin InReach, and I use this when I go out in the wilderness, or when I know I'm going somewhere where I need to be in contact if something happens to me for an emergency. And the reason for that is it's basically a satellite texting device in addition to being a handheld GPS. So this one has a lot of different functions. The point today, though, is that it's a handheld GPS unit. This is like your traditional trail GPS for navigating in the field or recording your routes, making waypoints. This was what people really got into with geocaching, which was popular maybe 15, 20 years ago. Now it's not as popular. And this device is not differential capable, so its accuracy is between 2 and 10 meters, maybe even more in places where there's steep terrain or trees. It'll maintain a lock on satellites, but it just has a lot of multipath error, and it's not getting any differential correction. It's pretty simple. You need to make sure that you go in on any device that you're using and change the settings for the coordinate system and the units to be correct for your applications. The Garmin InReach itself has an SOS button on the side that you can press if you're in an emergency, and you can actually go in here and, in addition to taking waypoints, measuring routes, so it will measure your route in your backpack while you're walking along. It will also send text messages via satellite anywhere in the world, including South Pole, North Pole, anywhere there are satellites, this will send that. It might take up to an hour to send, just because you can imagine it's trying to send a text message. It's only a satellite device. That's just kind of an introduction to this. So we're going to go take a waypoint now and figure out the accuracy of that. Okay, I'm going to provide an introduction to RTK GPS systems. First, we have the traditional RTK with a permanent base station, RTK standing for real-time kinematic. So the basic RTK is the rover out in the field, which this person is holding on to. It's on top of a 2-meter rod, and it has this GPS unit on the top. And it's connected by radio link to a permanent base station, usually mounted to a building in some area. And traditional RTK would only have a connection to one base station. That GPS unit would be connected via satellite, and the base station, sorry, the rover would be connected via satellite. The base station would be in contact with the satellites as well. And the base station would have an incredibly accurate location. We're talking, it would know its spot on the planet accurate to less than a millimeter. And the way that they do that is via averaging for long periods of time. And so the rover is out in the field, it's connected via satellites, but it's also getting a differential correction from the base station. And the reason for that is there's a lot of atmospheric interference. There's just different concentrations of chemicals in the atmosphere and reflectance based off of if there's a lot of water vapor or clouds, that sort of thing, when you're out in the field just with the rover. So this base station provides that differential correction. And then the rover itself, the components aren't super important. In the past, there were more numerous components, and you'll see that later in this video, that there was a backpack and an antenna and all of that. These days, you won't have as many components even for a traditional RTK setup, but the rover itself is going to have the GPS receiver on the top of the pole, connected to some, and it would either have the computer on board or the computer would be in a backpack, and then the user would interface via a data collector. You can also have a traditional RTK setup where instead of having a base station mounted on a building, you can have a base station that you set up out in the field on a tripod, and that would sit there and average all day long in one spot. And not only is that base station have very good accuracy, like it's a very good GPS just for a field GPS, but it sits there and it averages all day its values, and so it essentially becomes a base station out in the field with sub-centimeter accuracy, and it functions the exact same way that a permanent base station would. The advantage to this setup is that if you're out in an area where there isn't a base station nearby, then you can just create your own base station and you can do all of your centimeter level accuracy GPS work and survey work. It usually is going to be slightly less accurate than a permanent base station, but older systems, this traditional RTK setup, which is very rarely used anymore, you really don't have, you can only operate within a certain area, because this radio signal, as of around the year 2000, this radio signal for most Trimble high-grade $10,000 GPS units or a similar brand would only be within about 3 or 4 or 5 miles. They would recommend to stay within about 10 kilometers of the base station, hence the need for this remote base setup. Nowadays, this has really become more popular in the last 5 years because it's just become so much more widely available. GPS infrastructure has allowed us to develop this technology called real-time network RTK or RTN, and it's all enabled via a setup of permanent base stations in cities across a wide area. So in this case, I drew out Davis, Winters, Woodland, Dixon, so the lower Sacramento Valley. You have all these permanent base stations mounted on buildings in a certain area, and you can actually have them out in the open too, but I've drawn these in locations where I know that they have a permanent base station. So if you are out in the field, you will have your rover GPS unit, which, similar to traditional RTK, has the receiver on the top of the stake, and it's connected via satellites, or it's connected to these satellites, and those satellites are still in contact with this network of base stations. Instead of just one base station near you, you are connected via a Wi-Fi hotspot. Around here, they use Verizon because it's a strong, reliable network in this area, and that wireless network is connected to all of these base stations. So this rover is in contact with this little Wi-Fi hotspot, which is subsequently in contact with the base stations. So it works much the same way as a traditional RTK. You're still getting the differential correction from the base stations, but in this case, it's an entire network of base stations, and you can go anywhere in the region and still get your sub-centimeter accuracy without having to be within 3 miles of a base station, and you don't need a remote base station to come with you and average the whole day. This is super handy. It's what I use for my research. I just go and I rent this technology, come out in the field. All I need is the stake with the GPS on the top, this mini little Wi-Fi hotspot, and then you still have the data collector. That's how you interface with the system. And this setup has better accuracy in many cases than some of the traditional RTK systems. And the reason for that is you can imagine that, let's say you are maybe 4 or 5 miles away from one of these cities. You're 4 or 5 miles away from the city of Winters. You're only going to be in contact with that one base station. You're kind of on the edge of the range. So the differential correction is already going to be 3 or 4 miles off, because the differential correction is only received for that exact precise location of the base station. So the further away you move from it, not only are you moving out of the radio link capabilities, but you're moving farther away from the accuracy of the differential correction. Let's say you only are in contact with that one base station. If you're using this modern RTK network, you can be in contact with multiple base stations that average out the actual unit, this very expensive, on the order of $30,000. This unit has an onboard computer that automatically averages and does the calculations for, essentially triangulates your signal and does the differential calculations on board, provides you with a real-time number on the order of less than 1/10 of a centimeter, so about 1 millimeter accuracy is usually what I was getting when I was doing my survey work. That's basically an introduction to the RTK systems, and I just wanted to describe these different setups so that you don't get confused if you see it on a diagram. They all basically work the same. You have a network of satellites. You have a rover that the person is actually, that's the GPS you're using in the field, and that rover is somehow connected to a base station or multiple base stations, whether it's a radio link or a cellular network, and that rover is getting differential corrections from those permanent stations where those points are precisely known. One more thing I do want to mention before we go is just that when you use an RTK GPS, no matter what type you're using, if you are taking points where it is very important to know the accuracy within at least a centimeter or maybe better accuracy, maybe perhaps down to 1 millimeter or 2, you're going to want to average. And so, for example, when I do my drone research and I go out in the field and I need to know the precise location of all of my ground control points, which is what I use to accurately georeference my imagery that my drone takes of say a 200-acre site. I place out 24 ground control points. I go out there with the RTK GPS, and I want to know that within about 1 millimeter or 2, or maybe a 1/2 centimeter if the accuracy isn't that great that day. What I would do is I would average the RTK unit over about 3 minutes. It takes a point every second, so that's about 180 points for 3 minutes, or 300 points for 5 minutes. Those are kind of the industry standards for what you would average. And then another thing to consider, going back to the, this real-time network system, is just that if you are out in an area, we have pretty good cell reception in the lower Sacramento Valley, but let's say you're in an area where you do have access to multiple base stations via a cellular network. but you're in an area where there's not really good cell phone signal. Perhaps it's spotty, perhaps it's really slow, and you're not getting that 5G network that you really need in order to do this real-time survey pretty well. What you can actually get is something called an RTK bridge, and basically all that does is it boosts your cellular signal. It's essentially, just think of it as a really intense Wi-Fi hotspot that gives you super powerful contact to that cellular network of base stations. That basically wraps up the concept of traditional and modern RTK use. So this is the 1998 Trimble RTK unit, RTK standing for real-time kinematic. The components here are going to be different than the components for a more modern rover, but in this case they had a backpack which had the computer itself on it, and this receives and calculates all of the measurements from the antenna, and then it sends it to the data collector here, which is how you interface with the device, and then it comes out this cable and goes up to our antenna. Everything with the new GPS units is wireless. One more thing we can compare the accuracy to the RTK with is georeferenced Google Earth imagery. So all of this has been georeferenced. This is imagery from, looks like August 11, 2019. And it's all been georeferenced using the Google Earth engine, which is an incredibly accurate, roughly 1 meter accuracy system using satellite imagery. So what we're going to do is go check out our point here on campus, our monument. And we can find this on Google Earth. It's this small little cover in the street. I'll zoom in quite a bit. And what we're going to do is create a waypoint and take the GPS reading of that. Just show you how to do that. Create a new place mark. We'll call it something appropriate like Google Earth waypoint. And I'm going to move it to precisely the center of that monument, okay? What appears to be on my screen, the center of that monument. And I'll click OK. And if we go and open that up again, go to Properties, it will show us the reading here pretty precisely. And then we can compare that accuracy to the accuracy of the actual RTK unit. That will give you an idea of the accuracy of the georeferenced Google Earth imagery.